In this video, we will investigate several more examples of calculating volumes via the washer method. So as a reminder, if you have some solid whose volume you'd like to calculate, the formula we came up with was a definite integral from a to b, so it's corresponding to the x values here with the solid, and what we need to integrate is a of x, where a of x is going to correspond to the area of the cross section of your solid at x. How I think of this maybe very intuitively is if my solid was just a big loaf of bread and I cut it with a knife at x, this right end would fall off, and that exposed cross section is the area a of x. So let's go ahead and look at an example. Let's determine the volume of the solid, which is obtained by revolving the region bounded by the curves y equals x squared and y squared equals 8x about the y-axis in this case. So let's go ahead and sketch a picture of what's going on. So we have the curve y equals x squared, so roughly speaking, a parabola opening upward. And I'm only drawing kind of the relevant portion that we are going to need here. And then we have y squared equals 8x. That's a parabola opening in the positive x direction. So roughly speaking, both of these are going through the origin. Looks something like this. And now that we are revolving around the y-axis, we're going to have to think about everything in terms of functions of y instead of just functions of x. So x squared equals y, we can write that as x equals, typically it would be plus or minus the square root of y, but we only have the part corresponding to positive x values. So x equals the square root of y. The second curve, if we just divide by 8, this would be x equals y squared over 8. And one thing we need to do immediately here is to find what y values are going to correspond to these points of intersection. By inspection, we see that we have 0, 0 as a point of intersection. But what is the y value of that second point of intersection? So we set the two curves equal to each other. So square root of y is equal to y squared over 8. We go ahead and we square both sides. So y is equal to y to the 4th over 64. So 64y equals y to the 4th. Putting everything on the same side, we would have y to the 4th minus 64y is equal to 0. And if we factor this, we'd have a y times y cubed minus 64 equals 0. So y equals 0, or y cubed minus 64 equals 0 means y equals 4. So this second point of intersection we have is going to have a y coordinate of 4. We're not necessarily concerned with what the x coordinate is, just the y coordinate. So this point is going to be something, comma, 4. So the volume of this solid of revolution is going to be the definite integral over how the y values are varying. So in our region, they're varying from 0 to 4. And then we're going to integrate a of y. Where recall what a of y is going to be. If we go to a y value between 0 and 4, a of y is going to correspond to whatever we get when it's revolved around the y-axis. So if we consider this graphical representation of what that's going to look like, it's once again going to be one of these washers. It's going to have a small radius, call it little r, and then a bigger radius, call it big R. And looking at our picture, we see the smaller radius is going to be the distance to the first curve, and the larger radius is going to be the distance to the larger curve. So the larger radius in this case is going to be square root y, and the smaller radius, little r, is going to be y squared over 8. So putting this together, a of y is going to be the area of the larger circle, pi times square root y squared, and we subtract away from it pi, the area of the smaller circle. So pi times the small r, y squared over 8 squared. And this is going to become pi y minus pi times y to the 4th all over 64. And once again, this is the new part of the problem, so it's very important to see that here we actually don't need to sketch the solid. What we need to do is think about the region. Because we have it around the y-axis with the washer method, we need everything in terms of y values, so 0 to 4. And then we need to think for a y value between 0 and 4, what is a of y going to be? Well, it's the area we get when we take this small segment and we rotate it around the y-axis. So it corresponds to the area of this washer. So plugging into our formula, this would be the definite integral from 0 to 4 of pi y minus pi times y to the 4th over 64. So the pi pulls out front. The antiderivative of y is 1/2 y squared. And the antiderivative of the next term would be 1 over 64 times 1/5 times y to the 5th from 0 to 4. We plug in a 4, so when we plug in a 4, we're going to have 1/2 of 16, which is 8. And then the next term, it seems like it's going to be a large or complicated number, but notice that we have a 64 on the bottom, which is 4 cubed, and we have a 4 getting plugged in, so 4 to the 5th over 4 cubed is just 4 squared. So it ends up being 16 over 5. And then we subtract away what we get when we plug in 0, which is simply 0. And if you simplify this, feel free to plug it into your calculator, what you're going to get is 24 over 5 times pi. And this represents the volume of the solid of revolution. So one last example using the washer method. Let's determine the volume of the solid which is obtained by rotating a region now about a line other than the x and y axes. So we're going to look at the region enclosed by y equals x and y equals x squared. So y equals x is this line, and y equals x squared, something like this. And I've only drawn kind of the relevant portion of the curve. And from 0 to the point where they intersect here, 1, the parabola y equals x squared is actually below the line. And what we would like to do is take this and rotate it about the line y equals 2. So our setup is going to be exactly the same. The volume of this solid of revolution, because it's about a horizontal line, everything in terms of x values, so 0 to 1, a of x dx. And what we need to do is determine if we pick an x value between 0 and 1 and think about the corresponding line segment in our region, what do we get when we rotate that around the line y equals 2? Well, if you imagine rotating this small segment around that line y equals 2, you're going to get one of these washers. You're going to have an inside radius and once again an outside radius. So we think a little r and a big R. Now that inside radius is going to be what? Whatever's closer to that line you're revolving about. So the inside radius would be this distance here. Now the outside radius is going to be a slightly larger distance. It's going to be big R. So to get little r, what we're doing is we're starting at the line y equals 2, and we're subtracting away x. To get to big R, we start at the line y equals 2, and we have to subtract away all the way to this smaller curve, x squared. So that tells us that a of x in this case is the area of the larger circle minus the area of the smaller circle. Which, if you simplify this down, we're going to have a pi times x to the 4th minus 5x squared plus 4x. So let's go ahead and put this all together, but first let me observe that whether we are rotating around the x-axis, the y-axis, or some other line, in this case y equals 2, our general approach is still the same. We sketch the enclosed region. Here we realize because it's going around a horizontal line, we're going to keep in terms of x values. So our region goes from 0 to 1, and we integrate a of x, where a of x corresponds to the cross section at x. So an x value between 0 and 1, what gets rotated around the line? In this case, it becomes a washer, and we've calculated out its area. So the desired volume is going to be pi, which is going to pull out front, the definite integral from 0 to 1 of x to the 4th minus 5x squared plus 4x. Anti-differentiating term by term, 1/5 x to the 5th minus 5/3 x cubed plus 4/2, which is 2 x squared, evaluate it from 1 to 0. When we plug in 1, we have 1/5 minus 5/3 plus 2. We subtract away what we get when we plug in 0, which is just 0. And this all ends up being, what, 1/5 minus 5/3 plus 2 is 8/15, all multiplied by pi. So keep in mind that we can form these solids of revolutions not just by rotating around an axis, but around any line. And for us, the type of lines that we would consider would be a horizontal line, y equals a number, or a vertical line, x equals a number.